Consider the piecewise function g of x, where g of x is x squared minus 4, so something that looks like this. But at 2, you don't count it. So there's a hole here at 2, whatever that 2 looks like. 2, there's some point called b. For what value of b is g of x continuous at x equals 2? Well, basically, I need to make sure that whatever b is, it fills in that spot right there. So let's set these guys equal to each other and plug in 2 for x. So we have x squared minus 4 equals b. Let's replace that x with 2, so we get 2 squared minus 4 equals b. 2 squared is 4, 4 minus 4 equals b. 0 is b, b is 0. So that if b is 0, and that fills in that guy right there, everything is good. The answer is C. Which of the following is not a removable point of discontinuity? So we have this function right here. A removable point of discontinuity is a fancy word for hole. Now, holes exist if you have a factor in the numerator that's exactly the same as a factor in the denominator. Not only that, but the multiplicity in the numerator has to be the same in the multiplicity of the denominator. So if I look at each of these, x would be 0, but the multiplicity is the same. That's a hole. I want the one that's not a hole. So 0 is not going to be my answer. I have 2 up here and 2 down here. Notice the multiplicity in the denominator is greater than the multiplicity in the numerator. That means that this guy is a vertical asymptote. So since the denominator's multiplicity is larger than the numerator's multiplicity, 2 is a vertical asymptote, which means 2 is not my removable point of discontinuity. But if I were to keep going, 3 and 3, same multiplicity, 3 is a whole. 4 and 4, same multiplicity, 4 is a whole. That wasn't even an option. 2 is my guy, and I'm sticking with it. If f of x equals ln of x, for x is between 0 and 2 and including 2, and if x squared ln of 2 exists between 2 and 4 and including 4, then the limit as x approaches 2 of f of x is what? So basically what I'm being asked here is I need to find the limit as x approaches the regular number. I'm given information to the left of that number and I'm given information to the right of that number. These two guys have to be exactly the same in order for the regular limit to exist. So consider this like the left-handed limit, consider this the right-handed limit. If the left-handed limit and the right-handed limit as x approaches 2 are exactly the same, then as x approaches 2 is also going to be that number. So let's find each one. We have ln of x. So if I were to plug in 2, I would get ln of 2. I'm not even going to bother trying to do any math right there. Okay. For this guy, I would get, if I plug in 2, 2 squared ln of 2, which is 4 ln of 2. Now, if I were to plug ln of 2 into a calculator, I would get some gross number. If I were to plug ln of 2 into a calculator, I would get some gross number, and multiplying 4 to it would be a bigger version of that number. So whatever this is, ln of 2 looks like that, and 4 ln of 2 is going to look like that. These guys do not match up at the same number. Therefore, the limit does not exist when the limit approaches regular old 2. So make sure that the left-handed side and the right-handed side match up. And if they don't, the limit does not exist. Take the limit as x approaches 4 of this, holy cow, quartic over x minus 4. Now, I can't plug in 4 because I would get something over 0, and I'm not even going to bother plugging in 4 up here because I'm assuming I'm also going to get 0. Maybe I will, maybe I won't. So this is what I'm going to do. I have a hunch that I'm going to have to do polynomial long division, and so I'm going to set up polynomial long division. You are already in order, so x to the 4th minus 7x cubed plus 12x squared plus 4x minus 16. Now, if you're a fan of synthetic division, by all means, use synthetic division. It's probably faster, but I like polynomial long division. I don't know why. Call me insane. X times x cubed is going to get me x to the fourth, so x cubed pops up here. Multiply x cubed to x minus 4, and I get x to the fourth minus 4x to the third. Subtract the entire row means you do minus plus, and that drops down negative 3x cubed. Drop down plus 12x squared. Repeat the process. X times negative 3x squared is going to get me negative 3x cubed. So let's multiply negative 3x squared to x minus 4. So that'll be negative 3x cubed plus 12x squared. Flip the signs. Ooh, this is nice. U becomes 0. Okay, so drop down 4x plus 4x. All right, x times what gets me 0? Well, nothing, so you're a big fat 0. So let's drop down the minus 16. X times what gives me 4x plus 4. So if I do 4 times x, I get 4x. If I do 4 times negative 4, I get negative 16. Thank goodness, because I have a remainder of 0. Now, why is that important? Well, since I have a remainder of 0, that means this guy is the same thing as x cubed minus 3x squared. I'm not going to write out plus 0 plus 4 times x minus 4 all over x minus 4. Now, if I didn't have a remainder of 0, life would be very complicated. But since it was, I can cross these out and now take the limit as x approaches 4 of that guy right there. So I plug in 4, which is going to be 4 cubed minus 3, 4 squared plus 4. 4 cubed is 64 minus 3 times 16. Ooh, 316 plus 4. That gets me 64 minus 48 plus 4. 64 plus 4, I'm just going to do this part because it's easier for me. It's going to be 68, and 68 minus 48 is 20. So yeah, I did this hoping that I would have a remainder of 0. My hopes were good. Maybe there's a different way to do it, but this is how I did it, and I'm sticking with it. Synthetic division also works too if you like that type of thing.